Hey everybody, Bill Sky, the assembly guy, and today we're going to do a follow-on video to my first floating point unit, x87 video, where we looked at the floating point stack. And what we're going to do today is we're going to take a look at what the XMM registers are in the floating point unit. It's brand new technology. Well, really not brand new, but might be brand new to you. And what it's used for, what those registers are used for. And we're going to do this in Windows because the Windows debugger is makes a little bit more sense when you look at them. Look at those registers. On Windows, they're XMM. On Linux, for some reason, they're YMM. I don't know why they did that, but they look a little bit different. So we just have a project here that is a Komanetsky functions project. We're not going to do much with those, but it might be something that might cause some problems during the demo. I'm looking forward to that and to show you how to fix it. So let's take a look at that new XMM technology in the floating point unit. It's just running bytes through the system as quickly as possible. Bytes, words, double words, whatever. And most of that is floating point. And to increase the speed of these applications, they wanted to create this new architecture inside of the CPU to allow it to better serve those programmers that are doing that type of technology. So we're going to take a look at that, and then what we're going to do is we're going to look at how you can program these just for the floating point unit. The XMM registers just as floating point because they're newer, they have more capabilities than the old x87. So let's get right to it. So the first thing I'm going to do is I'm going to actually show you a demonstration of how the XMM processor or registers within the floating point unit can actually be used to increase the speed of your application. So what I'm going to do is I'm going to create a float array here and just a bunch of doubles, and I'm just going to put some simple data here. Now I'm doing these strange numbers just so they're easy to identify. And then I'm going to create a temporary floating point number or variable. And I'm going to use the real 4 for this one. It's the same as define double, but I just want to show you how you can mix and match. And you'll see why I'm going to be using that temporary float. So really, this is just an array of 4 floating point numbers. Now what I could have done, I just could have say define double 111.1, 222.22, 333.33. But you can't do that in Linux, and I try to code in such a way that's compatible across operating systems. Okay, so there we go. So now I'm using the Komanetsky 64-bit library template so I can do some prints. But I don't think we're going to be doing a lot of prints in this demonstration. So now, before we move on, if you haven't looked at the x87 video, which was the one previous to this one, there will be a link to that in the description of this video. Please go ahead and take a look at that if you don't know about x87 floating point, because we're going to be doing something in here in this demonstration that you kind of need to know that. So just kind of pause this, go and take a look at that one. It's a long video, but it's well worth watching it, and I did index or chapterize, if that's a word. I did set up chapters for that video so it can help you out. So the first thing I'm going to do is I'm going to initialize the floating point unit. And here's what I want to do is I want to take this array of numbers and I just want to multiply them by 2. That's all I want to do. So I already wrote this code, so I'm just going to type it in again. So I'm going to initialize the floating point unit. I'm going to move the address of my float array into RSI. I'm going to move into RCX4. RCX is going to be used as our loop counter. Remember, this is 64-bit, so we're not using ECX, we're using RCX. And then I'm going to create a loop. And the way that you have to do that is I can't move this number directly into a floating point, into the floating point stack for x87. So what I'm going to do is I'm going to move into EAX the dereferenced RSI. Now I couldn't, normally what you should be able to do is I should be able to do something like this, but I can't. And actually this should be a D word. The syntax of FLD will not let me do it. I can only do an FLD from another floating point register or from memory. So I can't do this. So what I'm going to do is I'm going to load the value of RSI that RSI is pointing to, which is 111.11 into EAX. I'm going to move into temp float EAX. So what I'm doing is I'm transferring the data from here into EAX. That's what I'm doing there. Actually, no, I'm transferring it. I'm transferring 111.11 into EAX, and I'm moving 111.11 into temp float. And remember, it doesn't matter if it's a floating point. It's just a bunch of bits, okay? So I'm going to move that into temp float, and then I'm going to load temp float into the FPU. I'm going to then load ST0 back in. So what I'm doing is I'm putting 111.11 into the floating point unit stack, and then I'm putting ST0, which is 111.11, I'm putting that back in. So we're going to have 111.11 and 111.11. And then I'm going to add those together. And now I need to store that back. So what I'm going to do is I'm going to store it into temp float. I'm going to move that value back into ECX. I'm basically doing the opposite of what I did at the beginning of this loop. And then I'm going to move into RSI that value. So I'm copying it out of memory, putting it in my floating point unit. I'm then adding those two numbers together, and then I'm going to put it back into that location. And then I need to move on to the next value in the floating point array. So I'm going to add into RSI4 because each one of those are 4 bytes. And then I'm going to go ahead and loop on the sum loop. Now I totaled this up. I went to what they call a latency table, which shows all of the values, how long it takes each one of those statements to execute. And I came up with 116, I'm just going to say clock ticks. So to do this 4 times is going to take 116 clock ticks. Now I'm going to build that. Let's make sure that I don't have any errors. And then let's go in there and quickly debug it, and I'm going to show you what it's doing. Oh, I didn't put a breakpoint. I have to put a breakpoint there. So let's put the breakpoint on the F init. Okay, here we go. So now the first thing I want to do is I want to show you the registers. So I'm not showing them here. So I'm going to go up into debug. I'm going to go to Windows, and I'm going to take a look. Let's take a look at the registers. And here they are right here. Now these are all the general purpose registers, the integer registers. I'm going to right click on it, and I'm going to click on floating point. Here's all the x87 registers. I'm going to right click again and click on MMX. And you can see our MMX registers. Okay, I can right click on that and say I also want to see the SSE registers. Here's XMM0. So these are pretty much all of the registers that you'll use. And you can see that there's 0 through 15 registers. And these are all floating point registers. They're 128 bits wide. And they can, why 128 bits? I mean, one of the largest floating point numbers that you're going to use ever is 64 bits. Why 128 bits? That's double 64 bits. Well, the demonstration I just did right here, where I'm going through and I'm going to multiply each one of these floating point numbers by 2, you can pretend that those might be 4 numbers that we pulled off of a graphic file or off of a video or off of audio. We loaded them up into an array, and now we're going to process them by multiplying each one by 2. I don't know, maybe we're increasing the brightness by 2, maybe we're changing the contrast by 2, I don't know. It's a silly little exercise, but I'm showing you how you normally would have to do it without the MMX or the XMM registers. So here's what we're doing here. So now I'm going to go up here into debug, I'm going to go to Windows, and I'm going to go down here to memory, because I want to see the memory. And what I'm going to do is, I'm going to take a look at float array. So I'm going to say ampersand float array. Okay, these are double words. So I'm going to right click, and I'm going to say 4-byte integers. And then I'm going to say, let's say 32-bit floating point. And so here's our numbers in memory. So there's 111.11, 222.22, 333.33, and there's 444.44. Now, if you're noticing that these are not exactly those values, you might want to go back to the x87 FPU video, because the FPU cannot store all floating point values 100% accurately in memory or in the CPU. So that's why they look kind of funny. So, but the FPU will round up. So go ahead and take a look at that video again if you haven't. All right. So now I can switch between registers and memory. So let's see what happens. So I'm going to go ahead and initialize. I'm going to move the address of the array into RSI. I'm going to move 4 into RCX. I'm then going to grab the first item, put it into EAX, and then put it into my temporary float, and then I'm going to load that temporary float into the x87 register pool. So I'm going to go back to registers. So we're going to be looking here, and there's 111.11. You see it's in scientific notation, so, or exponential notation, so that worked. So now what I'm going to do is I'm going to load it again. You can see how we have 111.11 over here and 111.11 over there. I'm then going to add those together. Now we have 222.22. Now I'm going to save them back into the array. So I'm going to go back to memory. And there it is. So we took that number and basically multiplied it by 2 by just adding them together. Now I could have done an fmul by 2. That would have been a little bit, I could have done that. It would have been the same number of clock ticks and instructions. And then we're going to go on to the next one. So what I'm going to do is I'm going to put a breakpoint right here, and we're just going to click continue. And you're going to watch these change. So now we're going to be working on 222.22. Now it's 444.44. We're going to be working on 333.33 at 666.888. So our algorithm is working. Our algorithm is multiplying each one by 2. Now think about this. If you have a video or an audio file that you need to multiply every number by 2, which is not unheard of, it's going to take 116 clock ticks for each one of those. If you have a 5 gigabyte video file, that's a lot. That's 5 gigabytes times 116 clock ticks. So it's going to take a little while for your processor to do that. Well, Intel knew that that was a problem. They knew it was a problem for multimedia developers, so they wanted to come up with some new way of doing this. So that's where the MMX or XMM registers come in. So what I'm going to do, I'm going to show you how to do all of this code in literally 3 lines of code. It's pretty awesome. So there's a whole group of new instructions. There's one called move APS, which just basically means move some single, oh, I'm having a senior moment here. Single precision floating points, move them as a group into a register inside of the FPU. That means that if we have 4 items that we want to move into a register, we can do it, and with a single statement. So I want to move into XMM0 float array. So what this statement is going to do is it's going to start at float array, and it's going to move all of the data that it can find there into XMM0, that register, until XMM0 is filled up. Now remember, XMM0 is 128 bits, right? So each one of these double words, each one of these is 32 bytes. So multiply 32 by 4, you get 128. So it's going to copy all 4 of those into the XMM register. Now, if I remember correctly, this statement right here is 4 clock ticks. Wow. You're already seeing a huge change because you don't have to go through a loop. It's just going to load them all in one shot. Then I'm going to say add PS XMM0 XMM0. So what I'm going to do there is I'm just going to say, hey, I want to take everything in the XMM0 register and just add it to itself. And that's basically the same thing as multiplying each one of those floating point numbers by 2. I looked that up as well, and that took 4 clock ticks. Now what I want to do is I want to save that back to the array. And yes, it's this easy. I'm going to move APS, and I'm going to move it into float array XMM0. This one right here also 4 clock ticks. So what is the total clock ticks for this? 12 clock ticks. It is almost 1/10 of the amount of CPU that's going to, or I should say FPU, that's going to be used to process that data. And it's going to do it all at once. Okay, so now we've got our code in here. And let me go over this one more time, what this is going to do. This first line is going to take everything starting at float array up to 128 bits and put it in the XMM0. Then we're going to add XMM0 to itself, and then we're going to save that back to the array. So let's go ahead and save and build this. Now something's going to happen here that I think is going to be kind of interesting. If you haven't seen my memory alignment video, it might be a good idea for you to take a look at that as well. Well, we already saw it happen, but it kind of got away from us here. So let me start this over again. And I'm going to put a breakpoint right there, and let's go ahead and run it. Okay, so you can see we've got our 222 or 444, so we went ahead and did all this code here. But watch what happens when I step over. We get this really strange error, exception unhandled. It really doesn't tell you a whole lot if you take a look at what it's doing. But I thought to myself, well, it's an access violation, so I wonder if this might be an alignment thing. So why did I think it was an alignment thing? Well, because I've got some just nothing, there's no aligned data here, just a bunch of bytes. So maybe the move APS statement must be aligned on a specific boundary. So what I'm going to do is I'm going to say align 16, because most of the time you align things on a 16-byte boundary. So I'm going to put align 16 right before my float array, and just like fx save and fx restore, they have to be aligned on a 16-byte boundary. So I'm going to go ahead and do that, and let's go ahead and build it. Now it shouldn't build any differently, and then I'm going to run it or debug it. So now we're there. Let's take a look at our array. There, this loop finished and it doubled each value here. Now I'm going to step over and let's see what happens. Boom. So the float array must be aligned on a 16-bit boundary. That's another example in x86-64 where a line might be important. So what this just did was this moved all of the data in float array, which was 4 double words, moved it in XMM. If I go to registers and we look at XMM, you can see that data here. Now it's pretty unreadable. If you went ahead and converted that into double words, you can see the first double word right here. The second double word is right there. The third one is right here. So if you went ahead and converted those to binary and then went ahead and converted them in a decimal floating point, they would be 111.11. I'm sorry, 222.22, 444.44, and so forth. So now we're going to add those together. So we're going to add XMM0 to itself. And again, it's a floating point. It's an IEEE 754 number, so it's kind of difficult to see. So we're going to go back to memory, and let's take a look. 222, 444, 666. Those should now be doubled when this saves it back to memory. And they are. They're now doubled. So instead of 222, it's 444. Instead of 444, it's 888. Instead of 666, it's 1333. So in 3 lines of code, in 12 clock ticks, I was actually able to process all 4 of those items in the array with only 3 statements and 12 clock ticks instead of 116. Holy moly. Now you might also be wondering, how did he get this latency information? How did he find out how fast each one of these runs? Well, I'm going to go up here in Google. I'm going to type in a latency table document. Let's say PDF. And let me see if I can find it. It's kind of a little bit difficult to find. I'll put a link to it in my video here. But there are some latency values. And let's look at this Agner Fog. Maybe this is the one I'm thinking about. Yep, this actually is it. So I did a search for latency table document PDF in the very first one. And you can see there's a lot of explanation here as to what each one of these are. but now you can see all the different processors. And you can then see over here, for entered instructions to move from a register to register, the latency is 1 clock tick. To move from memory, 8-bit memory, to an 8-bit register, it's 4 clock ticks. You can see that right there. 32-bit memory to 32-bit register is 3 clock ticks. I'm not sure what the high is there, but anyway, so you can see, or maybe that's a half. That's a half move. So you can see what each one of these totals up to, and that's how I came up with these numbers. So that's an overview of the MMX, why the MMX registers, or I should say XMM registers are there. It's to allow for audio and visual processing, quick processing. Instead of having to go through every single one, you can bring them into the processor in groups. There's a lot more to it than this, but that's an example of why XMM exists. So the next video I'm going to do is I'm going to do a video on how you can use the XMM registers to actually do floating point, just like we did with the x87 floating point unit, the FPU. Hope to see you at that video.